Okay, so in this video we'll be looking at Argand diagrams. Okay, Argand diagrams are just a way of representing complex numbers on a plane. So if you had a complex number 4 plus I, and I'm just going to write it down, 4 plus I, which is Z1, the real part is the 4, and the imaginary part is the number in front of the I, which is in this case 1. So what you plot is effectively just the point 4, 1. Make sure we call it a real axis and an imaginary axis. Okay, so the real parts go on the real axis, the imaginary parts go on the imaginary axis. So we're doing 4, 1, and put it down there, dot, and we label it Z1. So make sure you put down the dot, make sure you label it Z1. This one, well, all you'd be plotting would be minus 2, 2. Oops, moved half the screen. So yeah, we're plotting minus 2, 2 is our point. Okay, so where's minus 2, 2? Well, it's minus 2 on the imaginary axis. Sorry, minus 2 on the real axis and 2 on the imaginary axis. So it's here, dot, and we're calling it Z2. So that's Z2 plotted, Z1 plotted. What about 0? Well, that's Z3. Well, let's call it 0 plus 0I. So there's no real parts and no imaginary parts. And we'd get Z3 at the origin. And let's go purple for this one. Let's go Z4. I know they don't call it Z4, but just for the purpose of the example, we can call it Z4. So Z4 is equal to Z1 plus Z2. Well, what's Z1? It's 4 plus I, and Z2 is minus 2 plus 2i. We group them. Z4 is going to be 2 plus 3i, and the point that you would plot would be 2 plus 3. So this would be our Z4. Now, they also talk about, what color pen will I use? They also talk about this notation here, with a line either side of it. That means modulus, the modulus of Z1. What they're asking is, how long is that line there? That is the modulus. So this is Z1, is the modulus of Z1. It's the distance from the origin. Distance from origin. Okay, so you might notice that, well, we have a right angle triangle here. See the right angle triangle, right angle right here? And if I want to find this length, and it's directly opposite the right angle, this is called the hypotenuse. So we can use Pythagoras' theorem, okay, which would lead us on to a formula that we actually have for modulus. So this length here is going to be, well, let's call it the hypotenuse. We know the hypotenuse squared is equal to a squared plus b squared. This bit being a, this bit being b. If you want to just get the hypotenuse, then it will be the square root of a squared plus b squared. And that holds true for all complex numbers. If you have a complex number that is a plus bi and you want to get the modulus of it, all you do is get the square root of a plus b squared. So what was Z1? So the modulus of Z1 is going to be the square root of 4 squared plus 1 squared. The modulus of Z1 is equal to the square root of 17. And you'd leave it like that. That's how you would finish it. It is the distance from the origin. Okay, we can apply the same formula to Z2, I think they asked us to find. So this distance here, the modulus of Z2 is going to be the square root of a squared plus b squared for Z2. So what was a? A was minus 2 squared plus 2 squared. the modulus of z2 is the square root of, what is it, 8? And that works out to be 2 root 2. So modulus of z2 is equal to 2 root 2. It's noteworthy why I didn't simplify the modulus of z1 any further, is because 17's a prime number. So it doesn't simplify any further, but 8 is not a prime number, so it does simplify. And the last one then, what's the modulus of this, of z4? The modulus of z4, which is the same as the modulus of z1 plus z2. Remember z4 I said was z1 plus z2. So I would first need to find the modulus of z4. What did I say z4 simplified down to when I found it? It was 2 plus 3. So even if it's a z1 plus a z2, make sure you simplify it. So 2 plus 3i, the modulus of it, modulus of z4, square root 2 squared plus 3 squared. That ends up being the square root of 2 squared is 4, 3 squared is 9, so it's the square root of 13. And why do I not simplify that any further? Or why? It just can't. I can't simplify it any further, but why do I know I can't? It's because 13 is a prime number, and if I put it in the calculator, I'd get no further. So a question like this then, if it asks you to plot them on an Argand diagram, it's very, very simple. We know z1 is going to be 2 plus i. 2 plus I, so that's z1. What else do we know? z2, minus 4 plus 3i, minus 1, minus 2, minus 3, minus 4. This is z2. Now, what does the line above this mean again? It's z1 bar. So what's z1 bar? z1 bar is equal to 2 plus I. No, it's not. That's what z1 is. What does the bar mean? It means that we change the sign of the imaginary part. So we're really going to plot 2 minus I. So this is 2 minus I. That's z1 bar. What you can see is that it has just flipped through the y-axis. A conjugate is a mirroring or a symmetry through the y-axis. Okay, so z2 bar will be flipped through the x-axis, not the y-axis, through the x-axis. Will be flipped through the x-axis, again, x-axis, or you could also call it the real axis. It is a mirroring or a flipping through the real axis. And we can double check that. Z2 is equal to minus 4 plus 3i. Z2 conjugate is minus 4 minus 3i. Minus 4 minus 3i. Z2 conjugate. And you can see it's as if it was flipped through the real axis or the x-axis. For a question like this, you'd want to make sure you just add z1 and z2 before you plot it. For a question like this, make sure you subtract them before you plot it. When they're beside each other like that, it means they're multiplied, so multiply them. And remember that I squared is equal to minus 1 when you are multiplying them together. And I'm just going to slow it down for this guy right here, because you need to remember it's 2 plus I all over, I'm going to do it in green, 2 plus I all over minus 4 plus 3i. Well, how do we deal with this? We multiply top and bottom. Remember, dividing a complex number by another complex number. Multiply top and bottom by the conjugate of the bottom. And we had a shortcut as well for how to multiply out the bottom lines. Okay, so you could multiply them out as if they were brackets in the bottom. Or you could remember that it's going to be minus 4 squared plus 3 squared. Okay, there's a shortcut to multiplying out the bottom line. The bottom line can be shortened to just a squared plus b squared. Now the top line you do have to multiply out the long way. So 2 by minus 4 is minus 8. 2 by minus 3i is minus 6i. I by minus 4 is minus 4i. I by minus 3 is minus 3i squared. What do we know about that minus 3i squared? I squared is minus 1. So it's minus 1 by minus 3 would be plus 3. So you end up with a minus 5 in total because of the minus 8. Minus 10i all over 4 squared is 16. 3 squared is 9, so all over 25. And what do we get? We get minus 5 over 25 minus 10 over 25i. That is minus 1/5 minus 2/5 I. You plot each of them separately. Now, I'm just not accurate enough, but you would plot the point minus 1 over 5 minus 2 over 5. Okay, 2 more little things to worry about. If we're multiplying by I, multiplying by I rotates the complex number (90° anti-clockwise), AC anti-clockwise, and multiplying by minus I rotates the complex number (90° clockwise). Okay, and I'll show you what happens with that. So if I had Z here, which is 3 plus 2i, 3 plus 2i is here. That's Z. If I were to multiply this by I, so I times 3 plus 2i would give me 3i plus 2i squared. But what do I know about I squared? It's minus 1, so this really is minus 2 plus 3i. Where is this? Minus 2 plus 3i? This is I times Z. And it's a little bit hard to notice, but if you were to draw this in, you can see that it is rotated. It's like a segment from a circle. What if I were to multiply by I again and get I squared? Well, I know I times Z is equal to minus 2 plus 3i from above. If I multiply that again, I squared, I just need to multiply by I one more time and get minus 2i plus 3i squared. What happens here? It goes to minus 3 minus 2i. Okay, where's minus 3 minus 2i? Minus 3 minus 2i is here. This is I squared Z. And again, you can see, I might as well do it in brown. It's rotated again 90° anti-clockwise. Take a wild guess what's going to happen here. It'll just be rotated again 90° anti-clockwise. Okay, so it was minus 3 minus 2i. It's going to be 2 minus 3i, I think is the last point. I cubed by Z. We'll bring us around to there. I'll draw it in a bit more of a curve down to here. What if I were to multiply by I one more time? I get back to the start. Remember we said I to the power of 4 in a previous video. What's I to the power of 4 is the same as 1. So multiplying anything by 1 will just leave you back at the start. Okay. So it's a cyclical relationship. If you kept multiplying by I, it would eventually just come back to where you began. One more thing to touch on then. It's very similar to what we were just talking about. If you were asked to write down three complex numbers that have the same modulus as Z1, remember to draw a quick little sketch. 2, 5, 2, 5, 2, 5, Z1. What else is going to have the same distance to the origin? Well, if you were to imagine you had a compass and could center it on the origin and make its radius the same as Z1, any point on that circle is going to have the same modulus. So this point right here, if you'd said was minus 2, it would be minus 2, 5, minus 2 plus 5i will be that one there. What about this point down here? Minus 2 minus 5i. About this one here? That'd be 2 minus 5i. Any other one that we could think of? You could say this point here, if you said this is 2 and this is 5, you could go 5 plus 2i. Over here, minus 5 plus 2i. Down here, minus 5 minus 2i. Over here, you could go 5 minus 2i. So there's loads of complex numbers that all have the same modulus. Or even, what is the modulus? 2 squared plus 5 squared, square rooted, the modulus of this, modulus of Z1. 4 plus 20, it's a square root of 29. So this point right here, this line is the square root of 29 long. How would you describe this point right here? That would just be square root of 29 plus 0i. This one here would be 0 plus the square root of 29i. This here would be minus the square root of 29 plus 0i. And this one here would be 0 minus the square root of 29i. So loads of complex numbers with the same modulus. Okay, so just to reiterate the real key points from today, that symbol means the modulus, and it's the distance from the origin. We know we have a formula for it, and we know it comes from Pythagoras. What else do we need to know? We need to know that a conjugate is just the mirroring through the x-axis or the real axis. Okay? Just the I-coordinate has changed, or the y-coordinate, maybe you'd like to think of it as. We know that multiplying by I rotates a complex number 90 degrees clockwise, and multiplying by, anti-clockwise, rotates at 90 degrees anti-clockwise, and multiplying by minus I rotates a complex number 90 degrees clockwise. The modulus stays the same. The modulus will change if you were to multiply by a real number, and I'll show you one quick example of that. If you were to take any complex number, let's say Z1 is equal to 2 plus 2i. So 2 plus 2i. Oops, no, Z1. Its modulus, the modulus of Z1, is the square root of 8, which is 2 root 2. So the length here is 2 root 2. That is the length, 2 root 2. What would 3 Z1 look like? Well, it would be 3 times each of those, so it would be 6 plus 6i. What would the modulus of this look like? The modulus of 3zi. Where's 6 plus 6i? 6 plus 6i. And I'm going to call it, let's say Z2 is equal to 3 times Z1, so let's call this Z2. The modulus of it would be the square root of 6 squared plus 6 squared. It's the square root of 36 plus 36, which is the square root of 72, which works out to be 6 root 2, if you put that into your calculator. Okay, 6 root 2. What have you noticed about the relationship here? this distance, this red distance, is 3 times this black distance. If you're multiplying a complex number by a real number, all you're doing is stretching it out along this line. We say that they're collinear. They exist on the same line. We could say this guy here is, say, Z3. Z3 is equal to 2 times Z1, which would be 4 plus 4i. And I know the modulus of Z3 straight away because it's twice as far out as Z1. So it's twice this modulus. So the modulus of Z3 is going to be 4 root 2. This works for fractions as well. You could say this one here, the point 1, 1, and say Z4 is equal to a half Z1. So you'd get 1 plus 1i Z4. The modulus is going to be root 2 because I've multiplied this by a half. So this length here is root 2 long. If you were to multiply by minus, let's say minus 2, so Z5 is equal to minus 2 times Z1, which you'd get minus 4 minus 4i. And this is down here, minus 4 minus 4i, there, Z5. The modulus is still the same though. How far from the origin is it? What's its distance from the origin? It's going to be the same as this distance here. So the modulus would be 4 root 2. This is 4 root 2. The modulus, and again you could bang that into the old modulus formula. Modulus of Z5 would be minus 4 squared plus minus 4 squared, square root of 32 works out to be 4 root 2. So this length again is 4 root 2 there.